Hi everyone, this is Lin Xiao. In this work, we propose an efficient, data-driven grasp synthesis method called UniGrasp. A good grasp depends on both the object and the gripper. We propose UniGrasp for grasping any object with any gripper. To achieve this, UniGrasp selects sets of contact points. It takes the object point count and the gripper URL file as the input, and sequentially output contact points. These contact points are both reachable by the gripper and in false closure. We evaluate UniGrasp method by grasping objects with various grippers in simulation and in the real-world experiments. UniGrasp achieves more than 90% grasp successful reads. UniGrasp is able to extract the gripper geometry and kinematics features and concatenate them with object feature in the encoding stage. We will explain this module first. We first use the URL file of the gripper to generate the point count of the gripper in given configurations. We use this point count as the input to train an autoencoder so that we can learn a low-dimensional Latin space that encodes the geometry of the robot hand in specific joint configurations. To describe the kinematics of the gripper, we first generate the gripper point counts in configurations at the joint limits. Take the two-fingered Sawyer gripper, for example. We generate point counts of the Sawyer at its maximum and minimum joint values, denoted as open and closed, together with the point count of half-open configurations. These configurations are able to describe the kinematics of the Sawyer gripper. We send these three-point counts into the gripper encoder and then combine their corresponding geometry features to finally output gripper feature. Here, our gripper features encode both geometry and kinematics of the gripper. In addition to gripper feature, we extract the object feature using PointNet++ network and concatenate it with the gripper feature. Then, the concatenated feature would be fed into a point set selection network to sequentially output contact points. Given the n-fingered gripper, our contact point selection network would have n stages. In stage 1, our model first predicts the probability for each object point. The probability is whether the point belongs to a contact point set. Then our model ranks the points of the object and selects the top K1 points. Conditioning on the first selected point. In stage 2, our model first predicts the probability of object point that whether the object point belongs to the same contact point set with the first selected object points. Our model then ranks the object points and selects the top K2 points. Conditioning on the first and the second selected point, in stage 3, our model predicts the probability that whether the third point belongs to the same contact point set with the first and the second selected point. Our model then ranks object points and selects the top K3 points. In the three-fingered gripper case, our model would terminate at stage 3, so the 3 selected points are the final contact point set selected by our model. We can control the robot to grasp the object after solving the inverse kinematics for those fingers. We first demonstrate the effectiveness of the learned gripper embedding space by visualizing the interpolation in the gripper feature space. We first generate the feature of 2 input point counts, then interpolate these 2 features and decode them into gripper point counts. You can see the top row shows the prismatic movement, and the middle rows represent the joint movement, and the bottom rows shows the geometry change between 2 types of 3-finger robot hands. Given the same object, our model would output different contact point sets according to the input gripper. The black points represents the object in top view. So the red, yellow, and green spheres indicates the contact point set selected by our model in stage 1, 2, and 3 respectively. The bottoms shows the robot hand. Note that for the left gripper, it could not open wide enough, and in the middle gripper, it could not close enough. But our method are able to generate the contact point sets that are adaptive to each robot hand's attributes. We use the UniGrasp method to grasp objects shown in the middle with 5 different grippers. We test our model by grasping novel objects with known grippers. Here, knowing grippers means we have trained our model with that gripper. When using the robotic 3-finger gripper, our model achieves 95% grasp successful read on 65 trials. We also test our model by grasping novel objects with novel grippers. We have not trained our model with this gripper. We first change the URL file of the Kinova 3-finger gripper to make it a new 2-fingered gripper. Our model achieves 93% grasp successful read on 60 trials. We also test our model on the illegal hand. Note that our model would select the 3 contact points for the thumb, index, and middle finger. Our model achieves 90% grasp successful read, while our baseline method can achieve only 40%. The failure cases are mainly due to imprecise perception, low friction, object deformation, and premature contacts. Thank you for your attention.